for the first time. So I was, about 5 years ago, I was asked to give a talk at an AIM workshop on compact moduli, where there were a bunch of people from the birational geometry side of the subject, and they wanted a sort of tame algebraic geometer who understood a little geometric invariant theory to say what you could do in the way of constructing moduli with GIT. And I introduced that talk by recalling the first time I ever heard Janusz Kolar speak, and he basically said, you know, geometric invariant theory is dead. Don't think about, yeah. So I was hoping to give this metaphor of, there's a famous Monty Python sketch in which John Cleese brings a dead parrot back to a pet shop where he has bought it. And Eric Idle, who's the owner of the pet shop, keeps telling him, no, it's not dead, it's only sleeping. You know, and so at the time I said, I tried to make the case that geometric invariant theory was only sleeping. And I think that, you know, what I'd like to sort of explain today is a number of lines, work of quite a few people, that sort of indicate that, you know, perhaps the parrot is starting to wake again. You know, so let me sort of the basic setup is we'll let Ks be the new canonical locus, so curves embedded by the nth power of their canonical model inside a corresponding new canonical Hilbert scheme. And that sits, you know, these new canonical models sit naturally inside some space of new canonical sections. Dimension you can easily write down by Riemann-Roch, but we won't need to. And then the point is that SLV acts on these spaces, and there's a parameter for that action, which is essentially a degree m, which you need to fix in order to linearize the action, and I'll review the details of how that goes in a second. And then the theorem of Gieseker's from about 74 or 75 that is referred to in the title simply says that the moduli space of stable curves of genus G can be constructed as the quotient, the GIT quotient of this K by SLV, if we take nu at least 5 and this linearization parameter large. And so I want to sort of start by reviewing a little bit what the sort of plan of that construction is, and then I want to follow essentially 3 or maybe 3.5 threads that have as their common theme kind of extending pieces of that construction. So one will be just change the moduli space, add some decorations such as mark points or stable maps. One will be to ask, and we've already heard in fact quite a bit about this one, and we'll hear more today, what if I remove these lower bounds and ask about lower canonical multiples? And at the very end, what if I actually don't require the degree to be large? And then the third theme will be that, in fact, the proof is indirect. You would think, you know, how should you construct a quotient by geometric invariant theory? You should prove that the things that exist downstairs have stable, the Hilbert points downstairs are stable, using the numerical criteria. But that's not really what Gieseker does. And so I'll report on sort of something very interesting that's actually not even on the archive yet, where this hole is filled in. So that's kind of the plan of the talk. So let's just recall the basic setup. So as I say, we have, so this we can sort of generalize. We don't need to think about pluricanonical curves, but I have some curve inside a projective space, which I think of as being given by some linear series and some sections. So n for me is going to be the dimension of V, and I'm going to work with affine indices because that makes the numbers come out a little bit easier. And then corresponding to this, we get a Hilbert point, which I'll just denote by square brackets of C, inside the corresponding Hilbert scheme, which depends on fixing the Hilbert polynomial of this embedding P. And I want to really be able to get rather concrete about that point. So I want to associate to the restriction exact sequence. So this is just the restriction of polynomials of degree m to sections of the mth power of the line bundle L, whose kernel will be elements of degree m piece of the ideal of C. And this is an exact sequence, at least if m is bigger than some lower bound that depends on the Hilbert polynomial in sight. And so having done that, I can view C as giving me an element in the Grassmannian of P of m dimensional quotients. That is, this is going to have dimension P of m of the polynomials of degree m on V. And that I want to think of as having a Plücker model sitting inside some projective space. So W will simply be the P of mth exterior power of the space of polynomials. And I really want coordinates here. So what is a Plücker coordinate? It's a wedge of this many P of m degree m monomials. But I want to just think of that as a set of P of m monomials. So Z sub alpha, Z sub A set of m, P of m degree m monomials. So then I simply take those monomials and I take their images in h naught of L to the mth on the curve. And the only question I really need to answer here is, what does it mean to say that that coordinate is non-zero at C? And so since we're taking the exterior product of those monomials, the condition is that their restrictions are linearly independent. And since I've cooked up the numbers so that the count of those is the dimension of this space, this is if and only if the monomials in A are a basis. So the numerical criterion now, if I write down a one-parameter subgroup, in SLV, the numerical criterion says that a point like C is stable if and only if every non-trivial lambda acts with both positive and negative weights on non-zero coordinates of C. And in fact, you can just require that it act with negative weights because of the possibility of reversing, of switching lambda and lambda inverse. So the condition that we can translate that condition using the associated filtration. So I'm going to assume that when I write this down that the weights are all distinct, but they don't need to be. So I have a sort of decreasing set of weights here. And what I need to do really is, this gives me a sort of weight filtration here on V, which let me assume the linear series is complete for the moment. And that will induce, by multiplication and restriction, a weight filtration on sections of L to the mth. And what we're interested in is to have a negative weight is the least weight of some basis of this space which is compatible with that filtration. So let me define that to be W lambda, or I'll sometimes think of this as an F lambda. So WF of M is simply the least weight of a basis of sections of L to the M. Okay, and then the translation of the numerical criterion in these terms is that for all lambda not equal to the trivial one parameter subgroup, W lambda of M is less than 0. So that's the translation of the condition that C is Hilbert stable. And I should put an M in here because changing the M changes the linearization of the action. So M Hilbert stable, but I'll often drop that if we think of things as fixed. And then less than or equal to is equivalent to semi-stable. So essentially proving stability amounts to sort of looking at these filtrations and seeing what they induce in powers of all of M and getting bounds for the number of sections of large weight. And so a few points to note are that this W lambda of M is in fact a polynomial of degree 2 in M, at least for M large, and we'll usually denote the leading coefficient of that polynomial in a normalized sense by EF or E lambda. Maybe I should put it E lambda plus lower terms. And so one way you can prove that this weight has a sign is to prove that this coefficient here has a sign. And that, in fact, is the standard way that people proceed. And then I'll refer to the concept of Chow stability occasionally, which I won't really write down carefully, but you should just think of Chow stability as letting M go to infinity. And in particular, this coefficient having a positive, negative, or 0 sign is equivalent to unstable, strictly semi-stable, or stable for Chow stability. So it's kind of a limit of this. And one other fact due to Hassett, Heon, and Lee is that if C is nice in a way that I won't specify too carefully, but then M minus 1 should divide this polynomial. And so that provides kind of a check for various calculations as to divisibility. So let me stop there and see if there are any questions about the setup. That's kind of a mouthful to swallow if you haven't heard it before, but I think most people in this room have, and it's really sort of serving to just set up the picture. Okay, so then the next, sort of the last piece of what I need to recall is kind of Gieseker's plan. Now, how are we going to construct moduli spaces using geometric invariant theory? So it's a little indirect. It has 3 steps. So the first step is that smooth objects in your problem are stable. So, for example, in the case of mg bar, what you show is that a curve embedded by a complete linear series of degree at least 2g plus 1 has a stable Hilbert point. Something like so. That's the first step. The second step is you prove something called, which I call a potential stability theorem. And what that should say is that if the degree of L with some kind of decoration, which will depend on the problem that we're considering, and I'll give an example in a second, divided by its h naught is close enough to 1. And so again, in your theorem, you have to specify what close enough to 1 means. Then several things happen, sort of singularities, bad singularities are are excluded. That's the first thing you exclude. Certain reducible configurations of curves are likewise excluded. And then the key thing is that there's a subcurve or slope stability inequality. And I'm going to write that as suppose I have a reducible curve C and a subcurve Y, then the decorated degree of L on Y divided by the space of sections of its restriction. So the corresponding quotient for the subcurve Y should be less than the same invariant for the entire curve C. And semi-stability should be less than or equal to. And I'm cheating a little bit here because, in fact, you need to take the degree quite large in order to write the inequality in this form. There's a more general form of this inequality which doesn't quite transform to this nice shape if the degree is lower. But this way of writing it is the way that appears in this work of Li and Wang that fills in the gap. So for example, in the construction of mg bar, you show that if something, then, sorry, I left out C is Hilbert semi-stable. Yeah, we left out. Then, so in the construction of mg bar, if I have anything which is semi-stable, then it cannot have worse singularities than ordinary nodes. It cannot have any rational tails or chains of rational curves of length greater than or equal to 1. And then you have this subcurve or slope inequality. And so in the mg bar case, we can say what this decorated degree is quite easily. It's the ordinary degree. Plus a half the number of points with which y intersects the complement of y. So it's sort of nodes that a y shares with the rest of the curves. You sort of distribute them 50-50 between the two sides in this degree. And so you get so this amounts to saying, another way to think of this is that what this forces actually, because an inequality here for y and the corresponding inequality for its complement, what they force, an easier way to think of this maybe, is to say that the degree of the line bundle L on any subcurve should be roughly proportional to its genus, within an error which is given by the number of nodes that lie on half on y and half on the other side. Okay, and then the third stage in Gieseker's program is a semi-stable replacement argument. So you notice we haven't proved that any nodal curves have stable Hilbert points. The way we do that is we start with a curve which satisfies the hypotheses of the potential stability theorem, and we smooth that out to a family over the disk. And then we take the punctured family. That's now a family of smooth curves which we know are stable, and so we can fill that into a family over the disk where the fibers sit inside the semi-stable locus. And so there'll be inside here some new special fiber which we know is semi-stable. And then you use the conditions you've built up in the potential stability theorem to check that the two central fibers are in fact the same, and so what you started with must have had a semi-stable Hilbert point. And so that's effective but rather unsatisfying. It's kind of a dishonest way to use GIT. Right? Okay, so and then and then there's one more sort of bonus of this approach, which is that the linearization we've fixed here gives us a natural choice of an ample line bundle on the Hilbert scheme. We can restrict that to this pluricanonical locus, and then it's invariant and it'll descend to the quotient. And so this produces naturally an ample class on the, let's say, I'm going to just give the formula for mg bar, and you can use a Grothendieck-Riemann-Roch calculation. This Mumford did in his enseignement paper, which is some multiple which won't really matter to us of 12 minus 4 over nu minus 4 over nu m plus 2 over nu m squared lambda minus delta, where lambda is the Hodge class and delta is the total class of the boundary. And I've written it in this funny way so that I can exhibit the slope as a function of the GIT parameters nu and mu. So that'll come up later on. Okay, so then let me start looking at the natural questions. Well, I mean, a sort of first natural question is, if we constructed the space mg bar this way, why don't we construct all the other moduli spaces of curves we like to work with this way? Okay, and mgn, weighted moduli spaces of weighted marked points, spaces of stable maps, pointed stable maps, and so forth. And you know, I think everybody just thought that this had been done for a long time until people started to sort of try and look it up and discovered that, in fact, it hadn't been done. And then they thought, oh, well, this will be easy, and it turns out it's not. Okay, so let's call this decorating the curve. And what it turns out is that the techniques used by Gieseker in step 1 to prove that smooth objects are stable are not sharp enough. So we need new ideas for step 1. Okay, and so that so people did start to think about this. So the first result is due to David Swinarski in about 2003 in a master's thesis he wrote under Francis Kirwan, and he handled the case of unpointed stable maps. And that's really the one case that's easy, that does follow pretty much mutatis mutandi from Gieseker's proof, and where where even step 1 doesn't really require any new ideas. It gets a little more intricate, but you know, it's relatively straightforward. And then he went on. He wrote a thesis which he defended in 2008 with Michael Thaddeus and myself, in which he handled weighted pointed curves in the sense of Hassett. And so here there really is a need for something new in step 1, and I'll come back to that towards the end of the talk. I won't say anything about what he did there now, but I mean, he had one key idea there. And then in the interim, another student of Kirwan's, Elizabeth Baldwin, had written a thesis on pointed stable maps, and they together wrote up a paper which has now appeared. I think it came out in about 2007. So this handles pointed stable maps. And of course, as a special case where the target is a point, you get the spaces of pointed stable curves. So here, although you are following Gieseker's plan in step 2, things get quite delicate. I just won't. I mean, it's technically quite a bit different. It takes them about 40 pages in this paper. There are just many cases to handle. What Baldwin found was an incredibly clever way to finesse the difficulty in step 1. So that's all I'll really make a comment about. So, here we have this curve of genus G with n marked points, and we have some one parameter subgroup. And essentially what she does is take that curve and attach an elliptic tail at the last marked point. And then out of this data, cook up a related one-parameter subgroup, lambda primed. And when I first saw this, I thought this was just wrong, because there's no functoriality here. I mean, this is completely ad hoc. But the amazing thing is that you can show is that this C prime is lambda prime stable, implies that C is lambda stable. Okay, and so you have now a diagonal induction, because this C primed is a curve of genus G plus 1, but with one fewer marked points. So a diagonal induction takes you back to the unpointed case, which Swinarski had handled. And it's quite delicate because one issue that I won't really go into here is that when you add decorations, you need to add some extra factors. You can't parameterize just by a Hilbert scheme. You have to add some factors of P of V to hold the points, to parameterize the points. And every time you do that, that introduces a parameter in the choice of linearization. For the Hilbert scheme, there's a discrete set of linearizations depending on the degree you use to set up the Plucher model. But now you can continuously vary linearization parameters, saying how important is each point relative to each other. That's how you handle weighted points. But also how important are the points relative to the curve part of the picture. And it turns out that in all these, you need to balance the linearization parameters fairly carefully to come out with the quotient you want. And so here, when you do this, the one thing that happens is that you get from the linearization you were interested in here to a perturbation of the linearization that you thought you understood here. And you have to be careful that you sort of haven't crossed any walls in doing that. But that they take care of in the argument. So the argument is extremely clever. It's really not that difficult. So I mean, here I won't say too much more about this, but there's one obvious question, given that you need to, that what these results all tell us about sort of a central balanced linearization. I mean, a natural question is what models arise as quotients with respect to other linearizations. And so that's really a potentially huge question. I mean, I don't think anybody has any idea how many walls there are, what sorts of things you will see. So the only work that I'm aware of in this direction is there's a preprint of Raoul Ponderpandes from about 1995, which I do not believe has ever appeared in print. But in any case, he looks at the case where we give kind of epsilon weight to the points. That is, we almost but do not quite ignore the points. And then he comes up with a rather different compactification, which is reminiscent of a Fulton-McPherson configuration space. And this is relatively, this choice here gets rid of all the difficulty with proving that smooth things are stable, basically. But that's presumably there are lots of other interesting quotients somewhere out there in that picture. Okay, so that's sort of all I'll say about that. The next sort of thread I wanted to look at a little bit is less ample models constructed by GIT. And here we've already heard lots and lots about this in other talks in the KMS meeting, and we're going to hear more later today. And so perhaps there are certainly people in this room who know more about this than I do, but they will correct me kindly when I make mistakes, let's say. So Yeah, so let's ask the question. I mean, two questions. So what if the degree over the h naught is greater than or equal to 8/7? So 8/7 was in the close enough to 1 in Gieseker's argument for mg bar. Close enough to 1 meant less than 8/7. And so that another way to say this is, what if nu is less than 5? Notice that this ratio here for a new canonical model, it's 2 nu over 2 nu minus 1, so it's 1 plus 1 over 2 nu minus 1. So exactly at nu equals 4 or less, you violate that 8/7 inequality. Okay. So in fact, this was a question. This question did occur to Gieseker because he said a student, well, what should we expect? So in the proof of the potential stability theorem, where this hypothesis is used in a sharp way, is it's needed to show cusps, ordinary cusps, are destabilizing. So the first thing you'd expect is if you remove it, you're going to have to allow cusps as singularities in your quotient. And then on the other hand, so if I look at it from the reducing nu point of view, S4 M is, if you go back here, this formula, this is, if nu is 4, then what I get here is 11 plus some terms of order 1 over m, or minus some terms of order. It's actually negative. And, sorry, 4. And S3m is 32/3 minus terms of order 1 over m. And so these numbers here are less than 11, which is the slope of the ample cone in the lambda delta plane by the theorem of Kornalba and Harris. So we expect that we will no longer get an ample model. And in fact, what's known to happen at that slope is that a curve which you construct by taking a fixed curve of genus g minus 1 and adjoining an elliptic tail with varying j invariant. So in this way you produce a rational curve inside the moduli space, and that curve b is contracted by 11 lambda minus delta. So we sort of expect to lose elliptic tails in these quotients. And so those two expectations were verified by Schubert in about 1986. It was, and what he showed is, let me be sure I get the quantification right here, is that, for G at least 3, the three canonical, let's just say the nu equals 3 Chow quotient is a moduli space, which we heard about already in several talks. M bar G pseudostable of pseudostable curves. And that just means exactly what's predicted here, that you allow curves to have cusps and you prohibit them from having elliptic tails. Okay, so let me make a little digression that's slightly off my theme, but I have the opportunity to say a little bit about a paper that Donghoon Hyun and I wrote, and I don't think either of us have ever spoken about it anywhere. It's a sort of real footnote in this subject. But in the, so let me say first that, Brendan Hassett and Donghoon Hyun sort of recast this theorem in what I guess you could call its modern light. I mean, this theorem just was forgotten for almost 20 years. And then about 2003, they started asking the question, what are the log minimal models of mg bar? So this is really, this is the model associated to the proj of k of mg bar plus alpha times the boundary, typically for alpha between 0 and 1. And so this is a divisor class whose slope is 13 over 2 minus alpha. So for example, if I start at alpha equals 1, I get slope 13 over 1, so that's in the ample cone. As I gradually decrease, that becomes less and less ample, and at alpha equals 9/11, we hit S alpha equals 11, so this sort of critical slope where something has to get blown down. And so they showed that mg bar of 9/11, the sort of model associated to the proj of that thing, is nothing else than this pseudo-stable compactification of Schuberts. And then they went on to ask, well, what will be the set of values of alpha smaller than 9/11 where further birational changes occur? How can we produce in some way the corresponding models, and can we describe what sits in them as solutions to some kind of a moduli problem? Well, I'll come back to that in a second, but I did say I want to digress because in this paper, in the original version, it's sort of, they refer to Schubert's result, and they state that he treated the cases nu equals 3 and 4. It's kind of funny that there's only nu equals 3. What happened to 4 there, right? And in fact, a couple of years ago, in a Festschrift for Hartshorn, Gieseker was discussing recent developments, and he said the same thing. But if you go look at the paper, it's only nu equals 3 there. And Swinarski said, where was the part where he does nu equals 4? Well, he didn't, is the answer. And we can say why, because he was actually working with these Chow quotients. And so in Schuberts' argument, what he needs, the instability of elliptic tails. Okay, and his argument works fine for nu equals 3, but for nu equals 4, it only shows that elliptic tails are not stable. And so this is kind of the worst example, blame Mumford for this, right? I mean, that not stable does not mean the same thing as unstable, right? I mean, at best, semi-stable, right? So what Donghoon and I did a couple of years ago now was sort of look at the argument more carefully, work it out in the Hilbert case, and what we show is that elliptic tails are nu equals 3 and 4, m sufficiently large, Hilbert unstable, and nu equals 4, Chow strictly semi-stable. So this is the problem. This strict semi-stability was the problem that got in Schubert's way. G4. If he'd worked with the Hilbert scheme, he would have been, in fact, okay. And cusps are again for the same situations, Hilbert stable, and nu equals 4, they're also Chow strictly semi-stable.
So what kind of model do you check for?
Well, that's coming, yeah. So in fact, I mean, this is a really nice example because in these, for the correct lambda that you look at to analyze these, what you find is that the weight polynomial is either, depending on whether you're dealing with a cusp or an elliptic tail, plus or minus m minus 1. So that is as close to being Hilbert semi-stable as it's possible to get without actually being so, given the divisibility conditions on this, and so you needed. I mean, the leading coefficient is really 0, and that's what got in Schubert's way. And so then, to answer Radu's question, what kind of quotients do you get? So the nu equals 3 and 4 m large Hilbert quotients are what you'd expect, the pseudo-stable moduli space, and they're geometric. That is, orbits correspond to. But the nu equals 4 Chow quotient is isomorphic to mg bar, to this pseudo-stable moduli space. I'm getting my p's and my g's upside down. It's isomorphic, but there is some non-separation. So what you see something like a curve with an elliptic tail degenerating to a curve with a rational cuspidal tail, and that generalizes to the cuspidal curve. So typically, these are the closed orbits, and there's some separation. But as a space, you get the same thing. Okay. And then the next stage in this process, I won't say too much about this because I'm sure others who understand it better will say more, but in the Hassett and Hewlin approach, what they in a paper that appeared last year, they analyzed the next critical value, which is alpha equals 7/10. And so here we have a picture that for alpha 7/10 plus epsilon, what we get is, again, the Schubert space of pseudo-stable curves. And for alpha 7/10 minus a small epsilon, we get a space of quasi-stable curves in which basically, I'm going to simplify a little bit and say, over here, tack nodes are allowed and elliptic bridges. So a situation like this where we have a curve of genus 1 meeting the rest of the curve in 2 points are excluded. And there are some sort of degenerations of this you have to worry about. But that's the essential idea in there. And then in between these two spaces, there's mg bar of 7/10, which has a slightly different stability condition, but again allowing tack nodes and excluding elliptic bridges. I'll just refer you to the paper for the details. And from the point of view of Markov, well, we've already constructed this as these nu equals 3 and 4 GIT quotients. These are both nu equals 2 GIT quotients. This one is the Chow quotient, and these ones here are the Hilbert quotients for large M. So that's sort of the next stage in reducing the mu or going to less ample things. Okay. So the next stage in this process, you can use the F conjecture, which conjecturally characterizes the cone of curves of the moduli spaces mgn bar to make predictions about what the next alphas will arise and what things happen. And so I will simply say that the predictions are that the next things that will happen are at alpha. I can only remember the slope, so let me get the so alpha equals 2/3, which corresponds to slope 39/9, and alpha equals 19/29, which corresponds to slope 29/3. And you also get predictions as to what singularities appear and what configurations disappear. So here we get Ramfoid cusps, so local equation y squared equals x to the 5th, and we rule out Weierstrass tails. So that's a situation where I have a curve of genus G minus 2 joined to a curve of genus 2, and this point here is a Weierstrass point on the curve of genus 2. And then here you see the next singularity, y squared equals x to the 6th, and you exclude general genus 2 tails. And when you go back to this formula here, which I fortunately still have on the board, these again should arise as from the bicanonical Hilbert theory. But the difference is you now actually have to fix a small value of m. Actually, m equals 6 in the first case, and m equals 4.5 in the second case. So if you're getting bored, you can try to see if that checks out in those. And so that poses completely new problems. I mean, everything that's been done to prove that things are stable in step 1 requires sort of somehow showing that the leading coefficient has a sign. And that depends essentially on assuming that the linearization degree m is very large. Okay, and since I have attempted to pack about apparently 75 minutes of talk into an hour, I was going to explain a little bit, but I'll simply say that there's a recent preprint of Swinarski and myself, and I talked about this in Youngman's seminar last year, so many people here have heard a little bit about this, where we attempt by brute force to try to understand some of these for very special curves. And I will simply say that there's quite a bit of work to get a well-posed problem, but once you've done that, you can make calculations in lots of examples, and absolutely everything that's predicted here is seen in all the examples. For example, when you have, say, a Weierstrass tail of this type, you look at what should be the critical one-parameter subgroup, and you look at its function, and that function is exactly some leading coefficient times m minus 1 times m minus 6. So the stability goes from being stable in degrees above 6 to unstable in degrees below, and the same thing here. I mean, it certainly looks like the picture works rather well, although we're still rather far from being able to construct any quotients that might be useful in the log minimal model program. First of all, we can only handle low genus examples because we're doing things computationally. And right now what we're trying to do is analyze those examples deductively in the hope of getting... It's enough, in fact, to have one point one curve whose Hilbert point is stable, because the stable locus is open, and that at least allows you to do the semi-stable replacement argument to handle other things. But we don't have that in large genera. And then it's, in fact, these degrees are too small to work in the Hilbert scheme. And the setup that I had over there required lots of vanishing that only happens in degrees well above 6 in the examples we're interested in. And so you need to work with multi-graded Hilbert schemes that parameterize ideals and not subcurves. And there's a comparison between that scheme and the Hilbert scheme, but you need to do sort of a fair bit of work to make that comparison effective enough to construct a quotient. So I won't say too much more about that, except it's ongoing work, and there's a preprint on the archive that describes this in fair detail. Well, let me spend the last 10 minutes talking about something I think is really perhaps the most exciting part of the talk, and where my contribution is virtual, in the sense that I'm going to try to describe to you a better set of estimates for linear series. And I'd actually written down something pretty close to these about a year and a half ago, and I put them aside until Swinarski's thesis appeared. But meanwhile, Jun Li and Xiaowei Wang prompted by some questions I asked in a survey paper I wrote last year, started working on the same problem and came up with exactly the same estimates and then did all the combinatorics. So in some sense, I'm kind of happy I'm off the hook for all the hard work that we've done with this. But so what I'd like to close with is to explain an estimate that allows, so this is sort of, so this is Junli and Xiaowei Wang, and I guess Xiaowei told me that they were going to have something up real soon now, so maybe next month. So again, if the decorated degree over the h naught is sufficiently close to 1, and it really needs to be quite close. Their proof, I think, will make explicit how close it needs to be, but it is going to need to be very, very close to 1, and that's going to amount to saying that this degree has to be very, very large relative to the genus. Okay, and C is a nodal curve of genus G, then C is C has stable mth Hilbert point for M sufficiently large if and only if C is slope or subcurve stable. So the condition, so this in fact, in some sense, had been proven by Caporazzo in their thesis in '91, but again by an indirect semi-stable replacement argument. Here they are actually going to, the method is to verify the numerical criterion for these curves. So this is what's really new, is they're actually able to fill in that embarrassing lacuna and do the proof the right way for the first time. And I think their motivation is that, of course, Wang is well known for his theorem on balance that allows you to deduce from this stability of varieties of general type the existence of metrics of constant scalar curvature. And from the differential geometry side, there's no idea of how you would handle, for example, a surface of general type whose canonical model has rational double points. This only works for things, for smooth things. And so they wanted to use this as kind of a test case to see if they could, from the GIT, produce something that would be helpful in the, that would help them to give a criterion that would apply on the differential geometry side. Okay, so let me very quickly draw a couple of pictures to illustrate. So let's take a really toy case. I mean, I'll just try to illustrate in this very toy case. We have just 3 steps to our filtration where we put first 1, then 2, and then 3 base points on. So each of these is codimension 1. So here I'm just thinking of sections vanishing at Q1, vanishing at Q1 and Q2, and vanishing at Q1, Q2, and Q3. And we give the weights 3, 2, 1, and 0. Okay? So essentially what you need to do in estimating, improving stability of a Hilbert point, you need to estimate the dimension of the space of sections of L to the mth of a given weight. Okay, so for example, let's ask sections of L to the mth of co-weight, meaning weight less than the maximum m times 3 m. Let's look at that as an example and say, how big is that space? So what Gieseker does in his proof, both for curves and for surfaces of general type, is he says Well, I'm going to look at either the mth tensor power of V1, and so sections in there are all going to vanish to order m at Q1. And so this has codimension m. Or it might be smarter for me to look at V0 times V2 and take the m over 2 tensor power of that. Let's assume that m is even. So the sections in here will vanish at both Q1 and Q2 to order m over 2. And so again, Riemann-Roch tells you the codimension is m. And then after he's made these estimates, he gets a criterion, and at the level of the so you do some, so this is sort of phase 1, you do some geometric estimation. And then in phase 2, you feed this into some kind of a combinatorial argument. Okay, and at the phase where he sort of chooses the combinatorial argument, he picks which of these he's going to use. Okay, and so delaying that choice is why his criterion does not work in any of these other cases, and promoting it is essentially the common idea behind what allowed Swinarsky to prove his result, and it's what Li and Wang do. So let me say what the idea is. The idea is let's look at the span of V1 to the mth and V0, V2 to the mth. Okay, so these are all sections of co-weight m, but now we have, by taking suitable sections in here, we can either take, we have sections that vanish to order m at Q1 or to order half m at Q1 and Q2, but the span of this has codimension just m over 2. Because the intersection of these things has codimension 3/2 m over 2. So this is just linear algebra. And so there's something in Swinarsky's thesis, which is the key idea there, and the key idea that underlies all of this is the span lemma, which you essentially use to soup this up to a situation where you have many possible base points and many possible factors. And then when you have made all those estimates, so that's essentially the idea, is that Gieseker here has kind of thrown away a factor of 2. And it didn't matter, his estimates were good enough to handle smooth unpointed curves, but when you get extra decorations or you get nodes, nodes are twice as bad because the degrees can go down twice as fast. You need that factor of 2 back, basically, and other things. So let me just finish with a picture that will sort of illustrate what happens at the end of the whole process. So in the combinatorial picture, Gieseker would wind up using linear programming to estimate. So in this direction, we have the weights r, and in this direction, we have the orders of vanishing at certain points. So Gieseker would work with all of the 3 points at once. So he's got a little area that has a 2-2 where this is, the order of vanishing here is this is co-order of vanishing. So the order of vanishing here is 1 at this point, and then 2 at this point where we have weight 1, and then 0, 0. So this is a little triangle which is 0, 3. Okay. Get this right. Yeah, this is a little triangle which is 3 by 3, and so the area is 9/2. What essentially this idea of Swinarsky's does is it allows you to decouple the different base points. And so you wind up looking at 3 triangles, one for Q1 that goes from 0, 3 to 1, 0, one for Q2 that goes from 0, 2 to 1, 0, and one for Q3 which just goes from 0, 1 to 1, 0. And so those have areas 3/2 plus 2/2 plus 1/2. So what I get there is 6 halves instead of 9 halves. The difference, 3 halves, you should think of as R1 over 2. In other words, what this game allows you to do is pick up at the left end of these filtrations some constant amount times the biggest weight. And then you need to do combinatorics to sort of spread that out over the whole filtration in a way that allows you to prove that the weight filtration has the right sign. That part I haven't seen. So, but I think the essential idea is really just this idea that rather than choosing one of these, you should take the span of all of them. Okay, so maybe I hope that wasn't too vague, but given that I haven't actually seen the paper, that's probably as precise as I dare to be. And if anybody's really interested, I can explain how I think of actually proving that you get this kind of a picture. Okay, so thanks for your patience.